Okay. So, in the last class we discussed towards the end of last class the spherical polar coordinates and the cylindrical polar coordinates, and this is the general field of change of coordinates. And in today's class what I'll do is try to give an application of what we have done so far, and the application that we will see involves a change of coordinates. It involves the change it involves change of coordinates of a two body problem to the center of mass and relative coordinate system. Okay. Before we do that, let us recap what we talked. We said that the spherical polar coordinates, and I will be using this in the class today. So, I want to recap this part. So, spherical polar coordinates, in this we go from x, y and z to r, theta and phi, and the definitions are: r is equal to square root of x square plus y square plus z square, theta is equal to tan inverse square root of, you can write it as tan inverse of square root of x square plus y square divided by z, and phi is equal to tan inverse y by x. So, this is the way you transform, you write r, theta and phi in terms of x, y, z. Similarly, you can write x, y, z in terms of r, theta and phi, and we'll just write down the values. X is r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta. Okay. Now, I'm emphasizing these relations because these are the relations that you will use whenever you want to transform from one set of variables to another set of variables. And one set of transformations that you will do will involve writing derivatives with respect to x, y, z in terms of derivatives with respect to r, theta, phi. So, I just want to briefly mention how you will do this transformation. This is the usual calculus of any variables, okay, and I want to emphasize that when you do this transformation you have to be careful how you do it. So suppose I have d by dx and I want to write it in terms of derivatives with respect to r, derivatives with respect to theta and derivatives with respect to phi. Okay. Now, I will be taking d by dx of some function, and the function can be a function of x, y, z. Okay. Now, if wherever I have x I substitute this, wherever I have y I will substitute this, wherever I have z I substitute this value, then my function will go from being a function of x, y, z to a function of r, theta, phi, and I'll call it f prime, okay, r, theta, phi, okay, and I still have derivative with respect to x. Now, the point is how do you write this derivative with respect to x in terms of derivatives with respect to r, theta and phi. And to do this, you notice that here I have a function of many variables and I am taking differential with respect to some other variable, and so I use the chain rule for partial differential equations to write this in the form dou f prime by dou r into dou r by dou x. Okay, so the dependence on r will be seen in this term. Okay, and so this is like if I only had a function of r, then I would only have this, but then since I also have functions of theta and phi, I will have two other terms. Plus dou f prime by dou phi by dou x. Okay. So we have used the normal chain rule for partial differential equations, okay, and and for a function of many variables to write derivative with respect to x in terms of derivatives with respect to r, theta and phi. Similarly, I can write derivatives with respect to y and I can write derivatives with respect to z, okay, in terms of derivatives with respect to the other quantities. Now, it is very important that this should be written as a function of r, theta and phi and nothing else. It should be written as a function of r, theta and phi. There should not be any x, y or z appearing in this in f prime. Okay. Now you could ask a question, what about going the other way? So, suppose I had a function, I will call it g of r, theta, phi, and I am taking derivatives with respect to r of this function. Actually, this should be a partial derivative. And I'll just step back here and say why this should be a partial derivative. So, this should actually be a partial derivative, and we will look at the reasons why it should be a partial derivative. So, the reason it should be a partial derivative is that we want to take the derivative with respect to x, keeping y and z fixed. So, when I take this derivative, I keep y and z fixed. And I won't bother saying that when you take the derivative with respect to x, you have to keep y and z fixed, but that is understood. Okay. Now, in this case, here when I take the derivative with respect to r, I have to keep theta and phi fixed, and here when I take derivative of r with respect to x, I need to keep y and z fixed. Similarly, here I will keep r and phi fixed, and here I will keep y and z. Here again I will keep r and theta, and here y and z. Okay. So, the point is we will always deal with partial derivatives, and we will not bother writing these sub indices, so because it will make our notation a lot simpler. But the point is that when you are taking derivative of r with respect to x, you will keep y and z fixed, and that means your r has to be expressed as a function of x, y and z. Okay. So, you should use r as a function of x, y, z, you should use this relation. Okay. Now, similarly, when you write theta as a function of x, you should use this relation when you take derivative of theta with respect to x, and similarly when you take derivative of phi with respect to x, you should use this relation. Okay. And it is important to keep track of which variables you are differentiating with and which variables are kept constant, and that will also tell you which relations you should use here. Now similarly, if you had a partial derivative with respect to r, here the assumption is that theta and phi are kept fixed. So, this is at fixed theta and phi, and what we want to do is to write this in terms of derivatives with respect to x, y and z. So, you can follow exactly the same procedure. So, what you do is wherever you have r, you use this relation, wherever you have theta, you use this relation, wherever you have phi, you use this relation. So, you go from a function of r, theta, phi to another function of x, y, z. So, we will call this g prime of x, y, z, and now your derivative with respect to r can be expanded in a chain rule just like this. So, what you had is derivative with respect to r, keeping theta and phi fixed. So, you can write this as dou g prime by dou x. This is keeping y and z fixed into dou x by dou r. Okay. So, you are taking derivative with respect to r, and this is keeping theta and phi fixed, plus dou g prime by dou y into dou y by dou r plus dou g prime dou z by dou r. Okay. And as usual, here you will keep theta and phi fixed, here also you will keep theta and phi fixed. Now, if you want to calculate dou x by dou r, then you need x as a function of r, theta and phi. So, you should use this relation. Okay, so when you calculate dou x by dou r, you use this relation. When you calculate dou y by dou r, you use this relation, and when you calculate dou z by dou r, you should use this relation. Now remember, in this notation, it is not true that dou x by r is not equal to dou r by dou x. Okay, so this is very important to remember. It is not like the usual ordinary derivatives. In this case, a partial derivative of x with respect to r is not the same as partial derivative of r with respect to x, and the reason for that is that when you write this derivative, when you write dou x by dou r, then the variables that you are keeping fixed, you have to write x as a function of r, theta, phi. So the fixed variables are theta and phi. So when you take partial derivative with respect to r, you are keeping theta and phi fixed. Okay, and in this case, when you are taking partial derivative of r with respect to x, you have to keep y and z fixed. And in general, these two are not equal. Okay, they may be equal in some special cases, but in general, they are not the same. So for example, if I want to calculate dou x by dou r, then I will be using this relation. And so if you use that relation, what you get is dou x by dou r is equal to, this is in general, this is not true. In this particular case, what you will get is that dou x by dou r is just sin theta cos phi. In this case, dou r by dou x, if you use this relation, you will get 1 over 2 square root of x square plus y square plus z square, and you will get a 2x. So you will just get x divided by square root of x square plus y square plus z square. And the confusing part is that in this special case, these two seem to have the same value, because this is x by r, which is sin theta cos phi. So in general, this is not true. Okay, so that is why I am emphasizing that in general, you take derivative of one quantity with respect to another, and you do the same partial derivative, you won't get the same answer. But in the particular case, so in the particular case of x and r, these values seem identical. Okay. However, let us look at dou x by dou theta. So if you want to calculate dou x by dou theta, you use this relation, and what you will say is that this is equal to r cos theta cos phi. Okay. And if you take dou theta by dou x, so in this case you will get 1 over 1 plus, if you take the derivative of tan inverse, you will get 1 plus x square plus y square divided by z square times the derivative of this argument, and the derivative of that argument is just 1 over z into 2 divided by square root of x square plus y square into half square root of x square plus y square into 2x. Okay. So dou theta by dou x in this case will be is equal to z divided by x square plus y square plus z square z square into 1 over square root of x square plus y square. Okay. And you can easily show that this is not the same as this quantity. Okay. In fact, this has dimensions of r, whereas this has dimensions of 1 over length. So even dimensionally, these quantities are not the same. So it is important to keep in mind that this need not be true. Okay. So I again emphasize, need not be true be true for general variables. Okay. So anyway, at the end of this, what you get is that you can transform a function of x, y, z to a function of r theta phi. You can transform derivatives with respect to x, y, and z to derivatives with respect to r theta and phi, and with these transformation rules you can completely change from one coordinate system to another coordinate system. Okay. Here we have taken the example of spherical polar coordinates, but the same method of transformation of coordinates can be used for any two sets of coordinates. So here once again I emphasize that we have taken the special case of spherical polar coordinates, but if you go from x, y, z to some arbitrary coordinates, you can still use the same transformation rules. So we can go from a set of coordinates x, y, and z to another set of coordinates alpha, beta, gamma. Okay, so these are the new set of coordinates. So old coordinates to new coordinates. And when we do this transformation, we know how to transform functions of x, y, z to functions of alpha, beta, gamma, and vice versa. And we also know how to deal with derivatives involving x, y, z and write them in terms of derivatives involving alpha, beta, gamma. Okay. So let us take a particular example of this, and this is an example that you probably have seen in the quantum chemistry courses. It is related to the center of mass and relative coordinates. And this is a classic this is the classic way of solving a two body problem, converting a two body problem into single body problems. Okay. So let us consider a quantum mechanical system that consists of two particles. The two particles are particle 1 of mass m, m1, and particle 2 of mass m2. Okay. So and these two particles have an interaction between them. So the interaction potential, okay, so the potential of interaction of the two particles depends only on the scalar distance between them. So it depends only on x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square. It just depends on the square root. Okay. So this is the interaction potential. And when the interaction potential depends only on the scalar distance between the particles, this is the distance between the particles. And when you have this case where the interaction potential depends only on the distance between the particles, you say that this potential is called a central potential. Okay, so such a potential of interaction is called a central potential, and there are many such examples of central potentials. In fact all the potentials that we deal with are usually central potentials. Okay. So what does this look like? You have a particle of mass m1 and you have another particle of mass m2. This is particle 1, particle 2 of mass m2. Okay. Now the coordinates of this particle could be in the coordinate system. The coordinates of this particle are written as x1, y1, z1, and the coordinates of this particle are written as x2, y2, z2. Okay, all small letters here. Okay. So, now we have specified the system. If we specify the form of the potential, then we have completed the specification of the problem. So, now examples of examples of central potentials. So, we can say V is equal to half k r square. So, it is as though these two particles are connected by a spring of spring constant k, and so when you stretch the particles, the potential energy changes, and in fact more correctly what we will say is r minus some equilibrium length, r equilibrium length square. So, the spring has some equilibrium length, and if you stretch it beyond that, then the particles feel some force. The other example is if the interaction between the two particles is Coulombic in nature, then you can say V looks like, and it looks like if Q1 and Q2 are the charges on the particles, Q1 Q2 by R. Okay. So, where R is the distance between the particles, and depending on the sign of Q1 and Q2, it could be attractive or repulsive. So, these are examples that you will see in your courses on quantum chemistry, and what I want to show you is to take the general case of a two body problem, okay, where the interaction potential only depends on the distance between the particles. So, in other words, if I take these two particles, I keep the distance the same, but I place them in this way, okay. So long as I keep the distance the same, the energy of the system will not change, okay. So I can take this particle, put it here, I can take this particle, put it here, I can do all these things, and it won't change the energy of the system, and this is something that makes physical sense, okay. So it shouldn't matter which way the particles are oriented, so long as the distance between them is the same. Okay. So, what is typically done in your quantum chemistry courses is to solve what is called the time independent Schrodinger equation for this problem. And we will not go into solving the time independent Schrodinger equation for this problem, but you should be familiar with an object called the Hamiltonian, which appears in quantum chemistry. So, what we will do is we will write the Hamiltonian for this system in the old coordinates, and then see how we can transform that Hamiltonian into the new coordinates. Okay. So, we start with the Hamiltonian. The Hamiltonian, as you must be familiar from your quantum chemistry courses, is an operator, okay, is an operator for the total energy. So, the Hamiltonian can be written as in this case. So this is the total energy operator. So it involves the kinetic energy of particle 1, it will involve the kinetic energy of particle 2, and it will involve the interaction, the potential energy of interaction between the two particles. Okay. So I will write this as V12. This is kinetic energy of 1, kinetic energy of 2. This is the interaction potential energy. Okay. So the point is we know the form of the operator for kinetic energy of 1, and this form of operator in the x, y, z coordinates, or rather x1. Okay, let me get back to this. So the Hamiltonian is an operator that operates on the variables involving the positions of both the particles. So this operates on the positions of particle 1 and particle 2. Particle 1 has 3 position coordinates x 1, y 1, z 1. Particle 2 has three coordinates x 2, y 2, z 2. So, this Hamiltonian operator operates on these positions. Okay, so it operates on these positions, and it operates on functions of these positions. Okay. Now, what we want to do is to take this form and write it instead as something that operates on what are called the center of mass and relative coordinates. Okay. In order to do that, let us first look how the Hamiltonian looks for this 2 particle system, and you will be familiar with this. You will be able to write this as d square minus h cross square by 2 m 1 d square by d x 1 square plus d square by d y 1 square plus d square by d z 1 square. So, this is the kinetic energy of particle 1. Then you write the kinetic energy of particle 2 as minus h cross square by 2 m 2, and what you have is and in addition you have to have the interaction potential energy, and we will just write it as V12 of, and this is a function only of the scalar distance between the 2 particles. So, if the distance between the 2 particles is r, this is a function only of this distance, and this distance can be written in this form. So, V, which is a function of square root of and the operator for this is just the functional form of this. So, if this form is half k r minus r equilibrium square, the operator form of this will just be multiplying by half k into this square. Similarly, if this form involves a 1 over r, the operator form will also involve multiplying by 1 over r. Okay. So, this is the entire Hamiltonian, and what we will do in the next 15 or 20 minutes is to take this Hamiltonian and write it in terms of transformed variables. Okay. And the variables that we will choose to transform them are what are called the center of mass and relative coordinates. Okay. So, before we see how this is to be done, let us define the center of mass and relative coordinates. Okay. So, you can say that so our goal is to go from x 1 y 1 z 1 x 2 y 2 z 2 to 2 coordinates, and the 2 coordinates, one will be the center of mass coordinate. So, if the center of mass of this system is here, center of mass, and that will have coordinates capital X, capital Y, capital Z, and the other coordinate is the relative coordinate which we represent by r, that is x, y, z, little x, little y, little z. So, this is the transformation we are going to do, and we will see that next. Center of mass and relative coordinates, and once again let me remind you. So, we have 2 particles. This is the x coordinate. You have first particle located at x 1, y 1, z 1. This is particle 1. And particle 2 is located at x 2, y 2, z 2. Okay. And we are going to go to a system. This particle 1 has mass m 1, this has mass m 2. We are going to go to a coordinate system in which instead of using x 1, y 1, z 1, x 2, y 2, z 2, we will use the center of mass coordinate. So, if this is the center of mass, its coordinates are typically represented by capital X, capital Y, and capital Z, and we have the relative coordinates. So, this is r, and this is represented by little x, little y, little z. Okay. Okay. So the meaning of these will become clear when we define this transformation. So the transformation is defined in the following way: capital X coordinate is the coordinate of the center of mass of these two particles, and that is given by m1 x1 plus m2 x2 m2. Similarly, capital Y is given by and capital Z is given by okay. So these define the center of mass coordinates. So these three together are called the okay. So this tells where the center of mass of this two body system is located. Okay. Now if you want to write the Hamiltonian operator, okay, since we had 6 variables here, you need 3 more variables, and the other 3 variables are what are called the relative coordinates. They are given by little x is equal to x1 minus x2 to z1 minus z2. Okay. And these 3 are what are called the relative coordinates. Okay. So we have set up the problem now. We went from a coordinate system involving x1, y1 and z1 to a coordinate system involving x2, y2 and z2. Okay. So we went from a coordinate system involving these two to a coordinate system involving capital X, capital Y, capital Z and little x, little y, little z. So the next target is to write your Hamiltonian, which is written in terms of an operator on functions of x1, y1, z1, x2, y2, z2 to a Hamiltonian which can be written as an operator on functions of these 6 variables. Okay. So we want to go from here to a Hamiltonian which is a function of these 6 variables. So I'll just write it down here. So you want to go from H operating on x1, y1, z1, x2, y2, z2 to H operating on x, y, z, little x, little y, little z. Okay. So the question is how will we do this transformation, and the answer is that you will do exactly what we did when we went from center of mass to spherical polar coordinates. Only thing, instead of 3 coordinates, now you have to do it with 6 coordinates. Okay. So here we wrote capital X, capital Y, capital Z in terms of, and little x, little y, little z in terms of x1, x2, y1, y2 and z1, z2. Okay. What we want to do is to take this operator and transform from x1, y1, z1 to x2, y2, z2 to those coordinates. So whatever we have to write in terms of capital X, capital Y, capital Z, little x, little y, little z. Okay. So let's see how that is done. Center of mass and relative coordinates, and our target is to take the Hamiltonian which is written as a function of x1, y1, z1 and x2, y2, z2 as this is written in the form minus h cross square by 2 m1 d square by d x1 square minus h cross square 2 m2 plus v, which is a function of square root of Okay. So, we want to go from a function of x1 y1 z1 x2 y2 z2 to a function of x y z, and let me remind you once again that this is the kinetic energy of particle 1, this is the kinetic energy of particle 2, and this term is the interaction potential energy of the two particles. Okay. In order to do this, what we will do is that what we will say is that wherever we have d by dx1, we want to write it in terms of d by d capital X and in terms of d by d little x. Okay. So let's so we have the equation x is equal to m1 x1 plus m2 x2 divided by m1 plus m2. Okay, and we have little x is equal to x1 minus x2. Okay. So the first thing you will say is that if I have this involves d by d x1. So, if I want to express d by d x1 in terms of d by d capital X and d by d little x, okay, then I will write this as d by d x1 is equal to d by d capital X into d capital X by d x1 plus d by d little x into d little x by d x1. Okay. So here whatever function I had I can express using these two equations. I can express x1 in terms of capital X and little x, and x2 in terms of capital X and little x. So, I can write x1 as a function of x and capital X. I can write x2 as a function of little x and capital X. Okay. And once I have my function, this Hamiltonian operates on some function, and if I can write that function as a function of little x and capital X, okay, then I can use the chain rule for partial derivatives, which we used earlier, to write the derivative with respect to x1 in this form. Okay. And so if this operates on some function, it will operate on the same function here, and that function will appear here. Okay. So let's then the question is, what is this and what is this? Okay. And in order to calculate this, you will say that I am taking the partial derivative of capital X with respect to little x1. Okay. So that should keep all the other variables fixed. The other variables will be y1 z1 and x2 y2 z2. So if you do that, then I just have to take the derivative of this with respect to x1, keeping everything else fixed, and so I can write the, and if you take the derivative, you will just get m1 divided by m1 plus m2. Okay. So, you will get exactly just m1 divided by m1 plus m2. Similarly, if I take the derivative of little x with respect to x1, okay, little x with respect to x1, I will just get 1. Okay. So, then I can write d by d x1 is equal to m1 divided by m1 plus m2 d by d capital X plus d by d little x. Okay. So that takes care of d by d x1 here. Now, similarly, I can write d by d y1 as m1 by m1 plus m2 into d by dy plus d by dy. So, I can write d by dy 1 is equal to m1 m2 dou by dou capital Y plus dou by dou little y, and I can write d by d z1 as m1 Okay. So, I have expressed derivatives with respect to x1, y1 and z1 in terms of derivatives with respect to little capital X and little x, capital Y and little y, capital Z and little z. Let me, this is capital Z. Okay, so what I should have here is capital Z. Okay. Now, this completes only half the problem. The other half of the problem is to express derivatives with respect to x 2, y 2 and z 2 in terms of derivatives with respect to capital X and little x, and so we will do that right here. We do not I mean it should be fairly obvious. If I take the derivative with respect to x 2, okay, then what I will have is d by d capital X into dx by dx 2. Okay. So, partial of capital X with respect to x 2, and you can see from this expression that this is just m 2 divided by m 1 plus m 2. So, this will just be m 2 d by d capital X. So, once again, what the first term, if I had instead of x 1, if I had x 2, then the first term would be d by d capital X into d capital X by d x 2, okay, and that is just this expression. The second term would be d by d small x into d small x by d x 2, and so that you can show that d small x by d x 2, if you look at this expression, if I take the derivative with respect to x 2, then I will just get minus 1. Okay. So, then this second term will just look like minus d by dx, and similarly I can write d by d y 2 as m 2 divided by capital Y, and I can write d by d z 2 as m 2 Okay. So, this completes the first part of the exercises, where we wanted to express functions with respect to x 1, y 1 and z 1 and x 2, y 2, z 2 in terms of derivatives with respect to x, y, z, little x, little y, little z. Okay. Now, so the next part is to just take this expression, substitute it here. In order to do this, you have to calculate the second derivative. Okay. So, this gives us the first derivative. Now, the next task is to calculate the second derivative with respect to x 1, and if you do that, what you will see is that you will have two derivatives with respect to capital X, two derivatives with respect to small x, and one derivative which mixes capital X and small x. Okay. So, let me do that next. Okay. So, we have the first derivative. Now, we have to calculate the second derivative. So, if I take the second derivative, that is just like taking the derivative of this. So, if I do that, then I have dou by dou x 1 of m 1 over and if I go ahead and do this, then I write this as d by d capital X of the first derivative, that is m 1 into dx by dx 1. Okay. So, I just take this thing and put it here, plus I will get d by d little x of x into dx by dx 1. Okay, so I have the so I'm using the chain rule again for partial derivatives. So d by d x1 I am writing as d by d capital X into d capital X by dx1 plus d by d small x into d small x by dx1, and you already know these values. So I can write this as I can substitute for this, and I won't go into the details, but you can show that this is equal to m1 over m1 plus m2 square dou capital X square. Okay, so that is the first term, and the second term will be m2. So this will give me a quantity m1 over m1 plus m2, and what I'll have is I have a 1 d by dx and I have 1 d by d little x. So it is d square by d capital X to a little x, plus I'll have a term, and here I have m1 by m2. Now what I have is d by dx of so this quantity is just 1 again. So the first term will just be m1 over m1 plus m2 dou square by dou little x dou capital X, and the last term will just be d square by d x square. Okay, so you'll have these 4 terms. Now notice that in these 2 terms it is only the order of the differentiation that is changed, and if your function is a continuous function of both these variables, then the order of the differentiation does not matter. So I can write this as m1 plus m2 dou square by dou x square, m1 by m1 plus m2 square plus m1 twice m1 over m1 plus m2 dou square by dou x plus t square by dou little x square. Okay, so this whole thing is equal to dou square by dou x1 square. Okay, so you have 3 terms for dou square by dou x1 square. Similarly, you will have 3 terms for dou square by dou y1 square, and you will have 3 terms for dou square by dou z1 square, and again 3 terms for each of these. Okay. Now as far as the v goes, v can be expressed simply using x1 minus x2 equal to little x, y1 minus y2 equal to little y, and z1 minus z2 equal to little z in terms of x, y, z. Okay, so let's put all this together and see what we get, and what you'll realize is that what we get is something very familiar to it will be quite familiar to many of you. Okay, so when I put all this together, what I'll get is I'll get a Hamiltonian, which is a function of little x of capital X, capital Y, capital Z, little x, little y, little z. Okay, and each of these will have various terms. So when I take the second derivative with respect to x1, we saw 3 terms here, 3 terms here, and I won't. So what I'll do is I'll collect the various terms in convenient ways to write this in the following form. Plus m2 square d square by dx square into, so this is minus h cross square by 2 m1 into this plus okay. So this whole thing is just the contribution from this first term. Okay. Now you can show for yourself that the contribution from this term, from the x2 term, you will have a contribution that looks like m2. What you will get is m2 divided by m1 plus m2 square and then this will change to a minus sign. So, minus 2 because you remember in the derivative with respect to x2, okay, the component involving d by dx came with a minus sign. So, 2 m1 2 m2 and you will have okay. So, similarly you will have plus for y, z and z. So, you will have terms involving all these. Okay. So, we will not bother writing that. Okay. So, let us look at this. Let us look at this part. Now, if I add these two terms, here I have a 1 by m1, here I have 1 by m2. So, then m1 square becomes m1 and you have m2. So, you have m1 plus m2 divided by m1 plus m2 square, and so I can write this whole Hamiltonian as minus h cross square by 2, and so I have 1 over m1 plus m2 and m1 plus I have 1 over m1 plus m2 dou square by dou x square. Okay. Then what you notice is that these two terms will cancel each other, because here I am dividing by m1, here I am dividing by m2. So, I just get plus 1 over m1 plus m2 and I get minus 1 over m1 plus m2, and they will cancel each other. And if you take these two terms, they will give you just so I have d square by dx square 1 over m1 m2. And for those who are familiar, this term is called the center of mass, capital M, center of mass or the total mass, and this is called the reduced mass, or it's actually 1 over the reduced mass. So, 1 over reduced mass is 1 over m1 plus 1 over m2. So, this looks like 1 over reduced mass d square by dx square, and this 1 over total mass d square by d capital X square. Okay. And I will not go into the details of the remaining parts, but you can show that you can write similar expressions for y, okay, which will be exactly the same. Instead of d by dx, you will have d by dy, instead of d by d little x, you will have d by d little y, and similarly for z. And so you can finally write this Hamiltonian in this form. So you can finally write the same Hamiltonian as minus h cross square by 2 capital M dou square by dou capital X square plus dou square by dou capital Y square plus dou square by dou capital Z square minus h cross square by 2 mu dou square by dou little x square plus dou square by dou little y square plus dou square by dou little z square, plus you have the interaction potential. So, the interaction potential is just written as V, which is a function of square root of x square plus y square plus z square. Okay. So, we wrote the Hamiltonian from x1 y1 z1 x2 y2 z2 to coordinates involving capital X, capital Y, capital Z, little x, little y, little z, and this is the standard center of mass and relative coordinates that is used in your quantum chemistry courses.